Welcome back. In this module, we're going to get a little more statistical, a little more high-tech, hopefully not too much. In this module, I want to talk about the difference or the difference between research designs and statistical models. Really about designing a study and analyzing a study. My emphasis won't surprise you, I hope. I'm more interested in design, the early on design of quality research. We'll worry about the fancy modeling later on. Secondly, a point I'll make is that the best designed studies typically require the simplest of analyses. There's sort of a paradox here. It's so easy to get seduced into fancy statistical models. But in my experience, we only really need these fancy models when we have a poor research design. That's not always the case, but in general it is. This cartoon from the New Yorker always makes me laugh a little bit. You can see two gentlemen there were in front of some big, looks like some computer machine, and the statement is this. This machine then selects the likely equations from a complicated pattern of theoretical possibilities. It calculates them, and the correct answer is printed out. Then Miss Svensson files them God knows where, and we just can't find the thing again. Again, let's not be seduced by fancy statistical work. Let's do good quality designs with good quality research. One of the things I've learned about teaching applied statistics for so many years, that most people learn a little bit of statistics. That's important. It's about understanding uncertainty in this quite uncertain world. A few learn fancy statistical models. These are the dangerous people. Fewer still learn quality research designs. In the IRL, we want to help you with quality research designs. I'm going to argue constantly that this is more important than fancy models. In fact, I want to share with you that in my opinion, we want to seek a simple design with intense content. That is, content that can show us a definitive answer about how to address health disparities or improve population health. Paul Rosenbaum, the great statistician, has this wonderful quote. The quality and strength of evidence provided by a research study is determined largely by its design. Excellent methods of analysis will not salvage a poorly designed study. Aspects of the design include the framing of the questions, assessment of measures, bias, and precision. An observational study, I'll get into that, an observational study that begins by examining an outcome variable, the outcome itself, is a formless, undisciplined investigation that lacks design. The design anticipates analysis. Again, we want to focus on setting the study up from the get-go to provide a good answer, good causal inference, good effect identification, and so forth. There's all kinds of things we could worry about here: internal validity, external validity, statistical validity, and so many other kinds of validity. I want to just focus on a few for the point of this little mini online course. Here's some threats to internal validity, that is, getting the answer right. Temporal precedence. Does the intervention happen before the outcome? Does the cause precede the effect? Selection, largely understood as people choosing to be exposed or treated as opposed to taking anyone. Those who choose to buy red Ford cars probably like red Ford cars. Tough to ask them to be in a survey about whether they like blue cars because they're choosing red cars. History, exogenous events, maturation, this statistical thing called regression to the mean, people leaving our study called attrition, testing and instrumentation. We ask people questions so many times they begin to anticipate the answer, and all other kinds of related things. There's entire volumes written about threats to validity. Don't have to worry about them here, just have to be cognizant that they exist. External validity might be thought of as generalizability. Does what work in Chicago work in Boston, work in LA, work in rural Alabama? Does it work in Missouri? These are questions about external validity. We want to worry about interactions across space. Well, the people in southwestern Missouri tend to be different than those in LA, different social norms and customs, and perhaps slightly different worldview. How do these different environments change how our intervention for health disparities works, how effective it is? These are threats to external validity. When we think about doing things to improve health, I like to remember this sort of bumper sticker, and it says, "Dear Science, I beg you not to prove that any more of my pleasures will harm me." So much of what we do in public health can be kind of a bummer to a lot of people. Don't drink, don't smoke, wear a bike helmet. All this stuff can be good, but can also sort of ruin the creativity or the joys of eating some chocolate or having a wonderful midnight swim or something like that. So a little humor here about what we're trying to accomplish. Let's talk about experiments as one kind of design to begin with. The history of experiments really begins in the 16th century, especially with that old guy, Francis Bacon. Then, of course, Galileo's telescope and his prosecution. More recently, Bradford Hill's randomized clinical trial. This was for tuberculosis. And in more social science work, there's been several national, in the United States, income maintenance experiments. Experiments have been going on for a long time. What do we mean by an experiment? Now, let's get into that a little bit. First, the epistemological, or understanding of where knowledge comes from, point. Experiments are used to test our knowledge of the world and correct it if necessary. Going right back to the earlier modules of what our goal of science is to have a theory or proposition, test it rigorously, and then change our mind or update our minds if necessary. If what we think is true is not true, we should change our opinion. If it is true, we can proceed. This is the key epistemological point. What exactly is an experiment as we understand it today? There are two key points. One is we do something to some group. We're going to talk about people here. So we do something to a group of people. We might give them health insurance. We might give them lovely ice cream. We might get them to exercise. We might give them political power to organize in a community. We do something in the community. And we randomly assign some people to get that treatment and others not. These are two key parts of an experiment. An exogenous or outside treatment, exogenous means outside, and random assignment. Some people get treated, some people don't, and we decide not by their height or hair color, but by perhaps a flip of a coin. The flip of the coin is heads, the person gets treated, tails, they don't. This is an experiment. Now, will we do lots of experiments in the IRL program? Probably not, maybe some, but we can understand our research designs by understanding what a really good experiment is, and then see where our study differs. Interestingly, experiments work from a known cause to an effect. That is, it works from, hey, if I empower these people, their health will improve. That's different from an observational study where you observe people's health and say, how come? Was it because they were empowered? So an experiment goes from causes, known causes or hypothesized causes, and sees the effect. That's the key idea. Another word on this idea of exogenous. Exogenous and its cousin, endogenous, are different. Exogenous means from the outside, like a meteor, hopefully not crashing into the earth. Endogenous means happening within. So an endogenous intervention is perhaps a community group coming together to organize with their leaders and their followers and affecting change. This is wonderful, often to improve health, but the scientific credibility of replicating that is challenged because it's endogenous versus exogenous. Random, well, I hope random is pretty obvious. Random means by chance. and there's some deep mathematical and philosophical issues here, but random means by chance, like rolling some hopefully fair dice. Let me distinguish random from random. There's random sampling. I go out and I randomly sample people at the mall or the university or the community center. I just take some at random. That's random sampling. There's also random assignment, which is to say I've got a bunch of people, some I want to give the intervention and some not. That random assignment is still done by, say, a flip of a coin. This is a different idea than random sampling. Random sampling enhances external validity, generalizability. Random assignment enhances internal validity, that I get the correct answer for these particular people. That's the big difference. Random assignment, which is a key part of experiments, tends to balance what we call confounders, alternative explanations between the groups. If I've got a bunch of people and I assign them at random, chances are with enough people, there'll be the same number of males and females of each group, same number of taller and shorter people in each group, same number of people with this color, this, that, other thing, people with motivated to change, people not motivated to change, stuff that's hard to measure. Through random assignment, these get to be the same in both groups. Importantly, this only works when we can randomize a whole bunch of people. How many? It's tough to say. The more, the better. This is what we call inexpectation. Now you might think, oh, the same groups on average, same number of males and females and tall and short and this and that. Yes, because what the random assignment is doing is motivating the experimental framework, which is trying to mimic that idea of the counterfactual with those stick figures we spoke of earlier in the modules. So all this is of a piece. What we'd like is the counterfactual. Can't get it. So we try to run an experiment with an exogenous intervention and a random assignment in order to mimic as best as possible in the real world that counterfactual. That's the goal of trying to understand these research designs. We want to manipulate, in the best sense of the word, we want to intervene to really see what happens. We change the policy on labeling menus for calories, whatever else we're working on, and then see its health effects. This kind of policy intervention, sometimes called experimental manipulation, is always better to have. The old quip is we want to twist the lion's tail to reveal his secrets. I really don't want to touch the lion, but that's the metaphor. Now we can learn without manipulation, it's just more difficult. It requires more assumptions, or like in the physical sciences, well-established natural laws. We can understand, say, planetary orbits. In the social, human, medical sciences, there tends to be more upheaval or chaos or noise, and so those natural laws are harder to establish. That was experiments. Now an observational study is different. An experiment, we have an exogenous treatment and random assignment. In an observational study, depending on who you ask, we still might have an exogenous treatment, but the people are not assigned at random. So the girls might go here and the boys there, the young people here, the old people there. People are choosing what the exposure they want. This undermines the comparativeness of the two groups treated and untreated. It undermines our counterfactual framework, and therefore this kind of study requires more assumptions. Here's a little summary. In an experiment, we go from we try to find the effects of causes. We manipulate or change the treatment. We have a random assignment, and we rule out competing explanations through the design itself. In an observational study, we try to find the causes of effects. That is, we observe the differences in health and try to see what caused it, appreciating all kinds of things could have caused it because we didn't manipulate anything. There's no random assignment. People are deciding to choose, and I put choose in quotes, eat more McDonald's, exercise less, all of these things. we have to rule out competing explanations by analysis. Here's when we tend to need sophisticated statistical models. I mentioned an example earlier about a community coming together and solving a great problem. That is really super when it comes to solving that particular problem. It is less useful for solving it in other places unless we can figure out how that group came together. There might be one magnificent leader of that group. Can we find that same leader in other parts of the country or the world? So endogenous treatments that sort of form up can be really useful, just hard to evaluate them in a scientific framework. I want to talk briefly about some other kinds of research designs, just to wet the whistle, get us going a little bit, and how do we understand these things.